So we're going to talk about Gaussian surfaces today. So let's just remind ourselves of where we're at. We've been talking about electric fields and electric forces. So looking down from above, if I had a positive charge here and a negative charge there, I could draw a pattern of field lines. Now, any particular point as an electric field, but if you kind of draw a tangent to all those, so any particular point, let's take over here, any particular point as an electric field, and that point there has an electric field, and that point there has an electric field, and that point there would be somewhere in between. I could then take those points and I can draw a kind of contour line going through those points. And it's going in the direction of the line. So if you like, these electric field lines, for any given, these electric field vectors, for any given field line, it's like a tangent to the line at that point. So sometimes we'll talk about electric field and we mean the vector. And sometimes we'll talk about electric field and we'll mean the line pattern. Yeah? It's like, imagine, so it's like that. So there's a little bit of, you've got to get that clear in your head first of all. So what I'm drawing now is a field line pattern. It's where all the little arrows point. And the arrows will start from the positive and go to the negative. So the first one goes right across. And then if I imagine going from that point there, it's actually, I know it's going to arc around. You're going to do a lab on this today. And it goes like that. And then if it's symmetrical, so that's going to go like that. And that's going to go like that. And then even round here, we get this guy goes all the way around and comes in there. And then this guy would go all the way around and come in there. And even this point, this is symmetrically opposite. That's going to go off. But it's going to come back from the other side of the universe and go in there. So it's like, it looks like an apple core, yeah? And if I were to contrast this with, say, another important shape that we do, which is a metal, two metal plates. If I had positive, 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 and I had it next to a negative, 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 then what I'd find for my field lines in this case would be, my field lines would start from the positive and go to the negative, kind of like that. Nice and cross. Near the edge, when there's a lack of symmetry, you tend to get this edge effect. And in fact, in some high-performance systems, they'll actually work hard to try and avoid that. So two different patterns. I could, if you get fancy, let me just, I'm testing my, I'm being a bit risky here because these are, I don't have these in my head. I kind of have to figure them out as I go along, but let's have a go and see what I'm doing today. So if I had a positive and I had a positive and I had two negatives, then I could even visualize that. And the way I'd visualize it is I'd say, oh, hold on. This guy has twice as much charges individually, those two guys. So whereas this guy I'm going to do with 8 little lines. Is that right? 1, 2, 3, 4, 5, 6. I think that's 8 little lines. 2, 3, 4. Yeah, that's 8 little lines. And that guy has 8 little lines. Because this guy has twice as much charge, I'm going to do 16 little lines. I got this feeling already that I'm going to regret this, but. And it's going to be complicated. So there's going to be, let's have a look. This guy is going to want to go towards the positive, and it's probably going to be pushed a little bit away by that. So I would expect that to go something like that. And I'd expect that to go kind of something like that. I'd expect that to go kind of something like that. And then this guy, I think, is going to be billowing out here. And this guy, that guy is going to be coming in there. And then this guy, again, it's not going to go this way because this guy's going to push it away. So I suspect that guy's going to go even round there. And that guy's going to go, oh, around there. And this guy, well, it's going to go like that, I think. Maybe I'm wrong on that one. We'll see. And then this guy, well, this guy's going to kind of go straight across, and this guy's going to go like that, and this guy's going to kind of go like that. And this guy's going to, and then this guy's going to go like that, and this guy's going to go like that, and this guy's going to go like that. It's okay. And then this guy's going to go like that. I'll cheat. And then that's going to go like that, you know. And I wouldn't take my life on this, but it's kind of like, it's not unreasonable. And what you notice is that there are regions where if you were to count how many field arrows, how many field lines you had in a given surface, you'd have a fair number, but over here you'd have a lot less. Now with, 3 and 1, that's like not very many shades of grey. If I had 3,627 in the dark region and I had 17 in the other region, it becomes much more finely tuned. But the fact is, we can make apparatus which will enable us to plot out these patterns. And I worked for an electron microscope company, and their job was to push electrons into the finest beam possible. So they would create the electrons using a filament, just like in an old-fashioned light bulb, in a filament light bulb. And then they'd put around the electrons, they'd put around what's called a Wiener cap. And it had a very specific shape, had a hole in it. I'm drawing a cross-section through it. And when you replaced the filament, you had to put the Wiener cap back, and you had to center things. And there's a whole, it's where there's that operator skill can make an instrument run very smoothly or very roughly. When I took the job there, I was told that I'd given up being a scientist and I'd become a race car driver, because my job was, no matter what the instrument was like, my job was to make it perform and make it look effortless. And I started looking at other people in the industry, and I saw people, there's a classic thing where when you change the voltage, everything goes out of focus and you have to refocus. And I saw one of our competitors changing the voltage and using, he was sat, and he was basically had his hand on the desk, but inadvertently his hand was rubbing against the focus knob outside of his hand. And as he changed the voltage, he was adjusting the focus using the outside of his hand. And he would basically say, oh, it's easy, just change the focus. And the guy was going, that's amazing, normally you lose focus altogether. And you did, but he was, and is that honest or not? The customer could learn to do that, but it was deceptive, wasn't it? He wasn't doing that, he was doing that, so you couldn't see. So, there's a lot of art in instrumentation as well, but the science and the factory's job is to make as reproducible and reliable and stable system as possible. And one of the important things is how small a spot you can make, because the smaller the spot, the better the analysis. And the way they designed these things is that they would use iterative computer methods using basically the laws we've learned to plot out the electric field at all these points and make contour maps just like this, but a bit more complicated. And then they'd use programs to work out where the electrons would go. So you'd end up with these diagrams that look just like you draw, but very nicely done. And they're doing calculations on those diagrams. So this is not just textbook stuff. This is actually used in the business area. Physical analogies are always good. So let me just pause a little bit here. I'm going to get rid of that Wiener cap, and I'm going to show you. So for these two guys here, the way that I can visualize those two guys there is in the kind of field that we're comfortable with, which is a gravitational field. And I can tell you that a positive charge is like a mountaintop, and a negative charge is like a sinkhole. And positive charges, not electrons, but positive charges behave like boulders. So I can say, okay, let's do a three-dimensional drawing of what's going to happen. So let me just go back. I want to do one more little bit in red on that diagram. So I didn't do well, did I? Color pen. I want to just kind of give you a hint of there's the side of the mountain and there's the side of the sinkhole. It's going to be relatively hard to draw, but you're gonna maybe get a little bit out of it. So let's go to a third color. Let's go to purple. And I can imagine that mountain's got a whole bunch of contour lines going around it. And this sinkhole has a whole bunch of contour lines going into it. You know, like that. Does that make sense? Yeah. And then you basically roll boulders. You roll boulders, and that boulder's going to roll down here and go in there and go down to there. And that boulder's going to roll down here. It's going to cross that plane, and it's going to go into the sinkhole. If you play golf, you should be really good at this. And there's going to be one, comes around here, goes into there. And even this one around here, I know it sounds weird, but it kind of goes around and comes into there, because there's nowhere else for it to go, you know. It's not a perfectly... And then that one goes off, and it goes off, you know, to the east, and it comes back from the west, and, you know, goes in there. And if you look at this pattern, this three-dimensional pattern from above, if you took an aerial photograph of it, you'd see that pattern there. So the more we can you see how I want to know, if I want to know what an electron's going to do, all I have to do is pick a point and say, oh, that electron is like the opposite of a positive charge. So the force per unit charge that it will feel will be that big in that direction. It's not going to be following the black arrow because it's a negative charge for the electron. And this one out here, oh, it's going to be... So I can pick points in space, and by knowing the electric field, it's like I've got a map of the terrain in terms of electrostatic charge. Does that make sense? Now, in maps, we use contour lines. We use height lines. We don't have boulders rolling down hills. We have height lines. And that is, in truth, like a voltage. When you buy a 9-volt battery, that's the same voltage. So we tend to think in terms of, you know, the geographical, the geography equivalent to what we're doing is the height contour line. But, you know, if it's got a whole bunch of contour lines, you're going to roll down that hill. And that's what our electric field line is. So that's kind of where we're going. We got that visualization. And then along came Gauss, and Gauss said, you know, if we draw these maps well enough, then we should be able to do math on these maps. And so that's what he did. And recognizing that electric field is really, 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 really valuable, like a map, is really, 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 really valuable when you're trying to find your way about. The Gauss's law, Gauss's theorem, enables us to calculate the electric field at various points. So we're going to learn how to talk about and how to quantify the number of field lines using some kind of rules. And then we're going to learn how to use those ideas to develop a thing called Gauss's law. And then we're going to use Gauss's law to solve some problems. Highly symmetrical problems, but we're going to solve some problems. And all the problems are actually on the website. So if you go to not the ones where I give you the link to, but if you go to Bonaquisti on YouTube, they're all there. There's a whole bunch of them there. And you can just review how, there's only like 6 different possibilities that we ask you about. And I think they're all there. I'm not sure exactly, but I think they're all there. So that's where we're going today. So we're going to imagine drawing these maps and imagine basically saying, well, how many arrows do we need for a 2 coulomb charge or for a 5 coulomb charge, or, you know, what are the rules to drawing these so we all draw them the same way? And that's where we're going to begin. So the first thing to recognize is that we call the number of lines, or arrows, let's call them, flux, F-L-U-X, flux. We have a flux of arrows, a flux of electric field lines. It means the number of them. And what we can say is, let's make the rule, and let's say that the number of field lines passing through a surface which is at 90 degrees to the field lines is going to be the electric field times the area. Let's just make that rule. So we say, imagine a surface that is perpendicular to the field. So the field is there because of charges, and we're not even bothering to draw the charges anymore. We don't need them. All we need is the electric field caused by the charges. And we're going to put a card in the stream, and we're going to say, okay, well, how many lines go through it? Well, clearly, if I put the card perpendicular to the oncoming arrows, I'll capture a number of them. If I turn the card sideways, I'll get none of them. So I've got to be perpendicular. I can't just be at any old angle to the on-flow of the arrows, or else it's not going to make any sense. But if the card is at 90 degrees to the arrows, and if need be, I'll bend it. But if it is at 90 degrees to the arrows, then what we say is that imagine a surface that is perpendicular to the field direction. The electric field arrow density, that's the number of arrows per square meter, is proportional to the field magnitude. The product of the magnitude of the electric field, that's E, and the surface area is called the flux. So there's our rule. You know, that's in meters squared. This is in this is going to be in newtons per coulomb or volts per meter. There's two ways of doing it, and so we get our thing. So flux is not just a number. It's got some values. It's got some units to it. The electric flux is proportional to the number of electric field lines penetrating the surface. They're all imaginary, you know, but I'm saying it's proportional to the number of field lines. Okay. Now consider a surface that is not perpendicular to the direction, but is at some angle. Okay, so we need to do a bit of geometry. And in a way, this is trivial, but in a way, you know, you gotta. It's complicated but trivial. It's like, who cares about it? Well, we need to do it, but it's a bit messy because of language. Let's say I give you the angle between the perpendicular direction and the angle of my card. Then the area that I want is not the area of the card. It's the area of this perpendicular projection. And if I think about it, well, that's a bit like that. And if this was a hypotenuse A, and this is a right triangle, which it is, and I give you that angle, and I call that, I don't know, X, you would say X is equal to A. Would it be cosine theta or sine theta? Cosine. It would be cosine theta, wouldn't it? Yeah. Cosine theta. And so what we say here is, well, if our flux is equal to the electric field times this perpendicular area, this is our PP area, well, that just equals the flux, the electric field times our card area times the cosine of the angle, this angle theta. And from physics 1, we recognize that, when we have this one thing times another thing times the cosine of the angle between them, we used that before in work. That was a dot product. So, but that dot product links two vectors. Well, E is already a vector, so I'm happy about that, but the area is not. So the mathematicians in us say, let's make it an area. Let's just make a vector up. Well, what's this vector? The vector will have the magnitude of this surface area, of the card area, and be perpendicular to the surface. That's our rule. So A is a vector which is perpendicular to the card surface and has a size which is proportional to the card surface area. Yeah. Now the problem is, what about that way versus that way? We'll get to that in a minute. Which direction does this A point from? We'll get to in a minute, okay? But just go with it for a moment. The interesting thing is, if you look at the geometry of this, if that is my vector A, and that is my theta, what you'll find is, there's my field direction. What you'll find is that this angle theta here is the same as that angle theta there. So very quickly people say, don't worry about trying to visualize it. Just learn that it's E dot A and figure out how to work out what the A vector is. Don't worry about trying to do trig on this thing. Just do, oh, it's E dot A. And so what happens is this made-up concept of the area vector being normal to the surface of the Gaussian surface is overwhelming. People love it because it makes the problem so much easier. So let's think about this. We're doing math, making up vectors for diagrams that are on an abstract concept. I mean, this is, we're like out there, you know. Making up the field lines is a bit of a conceptual leap, and we're doing math on those things. And not only are we doing math on those things, we're making up a vector. That, you know, area is not a vector. Well, today it is. And it will be a vector in the future as well, because it's a very useful thing to do. And we can do all that because we're consistent and we follow. We know what we're doing and we do it the same way every time. Okay. So an electric field of 2 newtons per coulomb points in a positive x direction. What is the electric flux that passes through a 3 meter squared surface in the YZ plane? So let's just mark our axes. This is our x-axis, this is our y-axis, and this is our z-axis. And I have 3 meters. I like to draw them as circles. They don't have to be. You know, you can draw that if it pleases you. Doesn't matter about the arrows on the bottom corner. I could draw it more symmetrically. It doesn't matter. As long as it's in this YZ plane. And I recognize there's a 90 degrees between there and there. So my area is perpendicular to the surface. Then I can say E is equal to, I can say flux is equal to E times A, because they're perpendicular to each other. If you like, I can say EA cosine theta, you know, which equals E times A times the cosine of 90, which is 1. So that was the easy way, and then we made it a bit more general. And so flux is equal to E was 2, A is 3. Notice by being in standard SI units, it just takes care of itself, times 1, if you like, which equals 6. Now, I'm not finished. That's an answer that's breaking my heart. What's missing? Units. So, what are the units? It's going to be newtons per coulomb times meters squared. Yeah. So logically it comes from the field times the surface area. Newtons per coulomb times meters squared. Yes? Isn't cosine of 90 is 0? Cosine of 90 is 0. So what did I do? It's the oh, I'm sorry, duh. Thank you ever so much. You're a good person. You saved my bacon. There's my electric field. There's my area. It's cosine of 0. These two guys are in the same direction. So it's the angle between them, and the angle between them is 0.
So the angle between who?
Angle between the electric field line and the perpendicular to the surface is 0. Man, that's embarrassing, but I'll live.
So the surface is in the YZ plane, right?
And the surface is what? In the YZ plane. It's YZ plane. Yeah. Cool. Cool. It's funny how you make slips and you just glide through it. So that's that. So this says an electric flux of 7 newtons per coulomb points in the x direction. What is the electric flux through a surface that is 2 meters squared if the normal to the surface is inclined at 70 degrees elevation above the positive x-axis? So, whoa, a lot of words there. So there's our x, there's our y, there's our z. And the normal to the surface is inclined at 70 degrees elevation above the positive x-axis. So it's like that, isn't it? There's 70 degrees. So there's my area. This is my area vector, if you like. And this is my field vector. And I want to find out my flux. Okay, can you do that one, please? So I'm going to remember that flux is equal to E dot A, which equals E times A times the cosine of the angle. I'll leave you with that bit and let you get on with it. Okay, we're back, and I'm going to close this out. I'm going to stop this. Let's see what people said. Oh, it's thinking. Let's see what people said. Pretty well B. Let's have a look and see where that comes from. Well, let's have a look. My flux is equal to E, and E is 7 times A, and A we said was 2, and the angle between them is 70, so it's cosine of 70. So this would be, it's going to be 14 cosine 70, 14 cosine 70, and that's going to be 4.788, so 4.8. And it's going to be newtons per coulomb times meters squared, so it's that guy. Not so bad, yeah? Not so bad. Yes?
So we know that A is perpendicular to the surface, right?
That's by definition, yes.
What
By
about
definition.
Where do we get the direction of E?
As it says, 7 newtons points along the positive direction.
Oh, okay.
Yeah, cool. Yeah, cool.
All right.
Now,
There are two normals, though.
there are 2 normals.
Aren't there?
Yeah, one side, one
Two
the other.
normals, right?
Yeah, and I said I'll get to that later.
Okay.
Yeah.
So you did it.
I'm telling you which one it is. I'm just saying the direction. Later on we'll decide which normal are we talking about. Okay? It turns out if you do the other normal you get the same answer.
Yeah.
The angle is
You know.
180, right?
But we know it's 70 though.
Because I told you. Yeah.
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 Okay, got it.
Yeah. So, can you do this one? This is in IJK, please. Can you do that? So, let's get focused, because time is passing. Zoom recording. So, listen up, please. Thank you. So, let's just stop this, and let's do this. So, let's see what people are getting. Mainly B. Let's have a look. So, even though it is a three-dimensional thing, and I'm not going to try and draw it precisely, I'm just going to imagine it. So I'm going to say, oh, look, there's my area. My A vector is equal to, and I find it on here, and I go 3I plus 4J minus, I'm sorry about that, that's a minus, 2K meters squared. And then to get the idea, I'm just going to do my E vector at some other direction. I'm not going to try and make it correct in terms of my diagram, but I am going to do a diagram because I do want to make sure I'm visualizing. Newtons per coulomb, and then we say flux is equal to E dot A, and we say, well, that means that flux is equal to, and we write down the E, and it's 4I plus 2J plus 3K. and then we dot that, and I make my dots big, not dots, but dots, because I can't tell you how many times I have just not spotted that and forgot the cosine of the angle and all that kind of stuff. So, and that's going to be 3i plus 4j minus 2k. So then what you do is you say your flux is equal to, and you multiply for the dot product, you multiply your coefficients together. So that's 4 times 3. And then we add on to it the next pair of coefficients, which is 2 times 4. And then we add on to that our next set of coefficients, which is 3 times minus 2. So my flux is equal to 12 plus 8 plus minus 6. So my flux is equal to, is that 18? 12 and 8 makes 20, or 14? Yeah, 14. And the units are going to be in newtons per coulomb, meters squared, which is that guy. So we had two examples, one where I gave you the two magnitudes and the angle between. So I was thinking about that magnitude times the cosine of the angle between. And then the other example we did was where I gave you two ijk vectors and you did the dot product. Both work. In a test, I'm far more likely to give you an ijk for one of them and the magnitude and direction for the other. Why not? So rather than saying the electric field is that, I could say an electric field of 6 newtons per coulomb pointing in the neg z axis. I've got to make it relatively easy to write and to visualize. So if I did that, I'd have, let's draw this diagram again. If I did that, I'd have my A vector would be kind of like, 3i plus 4j minus 2k meters squared. But then I've got a very specific E vector, and the E vector would be in the negative z-axis, is in that direction. And it has a value, and it's basically no i's and no j's, but minus 6k's. So my sense is it's easier. You've got two choices when you're given a magnitude and a direction with an ijk. You've either got to go to the right or to the left. You could try and work out the magnitude of this guy and then try and work out the angle between these two guys, and you could use that side. But I think that's a very hard road to walk. It's much easier to work out the ijk, and then you got two ijk's, so you use the scalar approach. Your choice, and both will work, but I think one of them is just mathematically much more accessible than the other. Okay? So we've practiced doing ijk. We've practiced doing our flux calculation on a little card somewhere in an electric field. Electric field's uniform and all that kind of stuff. Let's make it a bit more interesting. So we're going to talk about electric flux in a non-uniform electric field. So now, what I mean by a non-uniform electric field is the electric field might be diverging, or it could be converging. I mean, stuff like this happens when you get point charges and real situations. So it's got to be a bit more complicated. The diagrams, we don't necessarily have to draw every arrow. I mean, we work basically, well, we'll see. So we're saying a non-uniform electric field, our equation works for small elements of the surface. We can't put a big card in there because the angles would come in at very different angles. The arrows would come in at very different angles to it. But if I imagine I could put a little card there and a little card there and a little card there, I can still have my 90-degree business for the stuff. We can define a vector, little bit of area, dA. So rather than the total area, this is a little bit of area, dA, whose magnitude represents the area of the ith element. Imagine this is a potato, and you get some of these little like like my daughter kind of played with these things. You kind of make these styrofoam little teddy bears and stuff like that, and you stick little gems on the outside, and it's made of a whole bunch of tiles, but you stick it on, and at the end it looks like a really kind of like armor-plated, you know, teddy bear or something. But that's what we do. We're doing a whole bunch of little tiles to sort out the shape. On the edge there'll be like there's a tile there, there's tiles at the back. And they're all flat tiles, but they've got different orientations to them. We have I of them, where we have a number which is big, so we'll call it I is 1, I is 2, I is 3, I is 4, whatever. And the direction of dA for this ith tile is perpendicular to the surface element, always. And so we say my little bit of flux, this is my little bit of flux going through this tile, is equal to my electric field going through the tile times a little bit of area for the electric tile, for the tile, multiplied by the angle between the two, cosine of the angle between the two. And that's the little bit of electric field going, the electric field going through that tile, dotted with its little area vector. Okay, so it's the same math. We can find the overall effect by summing all these things. So imagine doing this for every tile on this surface. And we get this limit as the little bit of area of my tiles goes to 0. So I'm using smaller and smaller tiles. My summation goes to the integral of E dot dA. It's a surface integral. So it's an integral of E dot dA. Now, let's pause for a second and try and resolve this thing we mentioned before about is the area vector going in one direction or the other. From an area, I could have my area vector going to the right or my area vector going to the left. So which is it? Let me sketch that. If I have a little card, maybe that's my area vector, but maybe that's my area vector. And I've got to have a rule to decide which way it is. And it depends on the angle to the electric field. What we say is, it depends upon, for an enclosed shape, what's pointing outwards and what's pointing inwards. The area vector always points out of an enclosed shape. And we're going to deal with enclosed shapes from now on. We just did that bit with a single card just to get practiced at doing flux. From now on, we're going to be using enclosed shapes. So it's going to point outwards, and it points outwards, and it points outwards. So by definition, the area vector points outside an enclosed shape, not inside the enclosed shape. And then we say, well, there's three choices, isn't there? There's three possibilities. There's maybe a situation where my angle between my area vector and my electric field is less than 90 degrees. And if I think back about the math, what that means is that my flux will be, my flux will be positive. Because it's a cosine, remember that all sine tan cos for the quadrants? All sine tan, is that right? Cos, did I do that right? I think I did that right. So for less than 90, then your cosine is positive, yeah? Have I got that right? I'm not sure I've got that right, but anyway. For greater than 90 degrees, then my cosine is going to be a negative value. Yep. Sure. So that's going to be negative. And for 90 degrees, it's going to be 0. The better way to do it is a cosine looks like that, doesn't it? Sure. That's 0. That's 90. That's 180. So for an angle that's between 0 and 90, I have a positive value for the cosine. That means that I call the flux positive. And for an angle between 90 and 180, I have a negative value for the cosine. So that means I call the flux negative. Now if we think about it, in this case, the electric field line is coming out of the surface. That's how I get an angle which is less than 90. When the surface is pointing away from the surface, the area is pointing away from the surface, and the flux line is coming out of the surface, that angle is less than 90. In this case, the electric field is pointing into the surface, and so my flux line is greater than 90. It's when your flux lines are when your field lines are coming out, it's going to be a positive flux. When your field lines are going in, it's going to be a negative flux. Agreed? So, what we say is the net flux, the overall flux through the surface is the sum, the integral of E dot dA. And remember that flux is proportional to the net number of lines leaving the surface or entering the surface. So we're going to do sums on this. And what we're going to do is we're going to link the net flux to the charge inside the surface. That's where we're headed. And then later on, we'll find the electric field by knowing the charge inside the surface. So it's like flux, electric field, and a surface combined using Gaussian surfaces. And initially we're going to prove the Gauss's law, but then we're going to use Gauss's law and we're going to use it to find the electric field. So that's the name of the game. Okay? That's really the impetus behind this. So what we say is, let's imagine a situation where we have a charge, and let's imagine a situation where we have a point of interest. Our little bit of area is at our point of interest. The point of interest can be where I tell you I'm interested in, but potentially anywhere in space. It's just a point of interest. There's no charge there, there's no nothing there, it's just a point of interest. And my job then is to imagine a closed Gaussian surface. Imagine constructing a surface of these little cards or tiles that is closed. And I can do whatever I like with it, but if I want to get a good answer simply, I'm going to use symmetries. Because if you think about, if you think about flux is equal to E dot dA, and you say, well, that's E times dA times the cosine of the angle between. And I'm going to do that for every little tile. It's really nice if the angle in between is constant and the angle in between is actually 0 degrees, because then the cosine becomes 1. So that's the ideal thing, is to have that be constant and equal to the cosine of it equal 1. And then the second other thing that's really useful is if for each little tile your electric field stays the same. Why have it changing? In principle, it can. Professor Soash would love it to change. He'd be giving you all these problems, take you 3 days to solve. And, word, page upon page of, because he's teaching you math. I'm teaching you physics. The math is my servant. It's not my master. Although my progress in physics will be limited by my math skills. So it's like, I can't just turn around and say, I'm sorry, I'm not doing differential equations. This area of physics is not going to include differential equations, because you need them when you need them, So, but I don't have to do everything from first principles like the mathematicians do. They must. They've got to show you all the steps. So occasionally I'll have a student who refuses to take any of the shortcuts. And they usually end up kind of like changing their mind. But, so there's nothing wrong with using symmetries. One of my, let me just pause this for a second, because. So we're back. So basically, you find in this section that we want to do a whole bunch of symmetries. So we're going to pick our Gaussian surface carefully. So in these problems later on, I'm not going to tell you what the Gaussian surface is. You're going to have to decide it. But there's only like 6 different patterns. So you just, if you invented it, it would be a stroke of real insight. If you do your homework, it's kind of like you can do it, So it's better to rely on homework practice rather than insight on a test. So you do your homework beforehand. So there is general relationship between the net flux through a closed surface, a Gaussian surface, and the charge that it encloses when E is parallel to dA. So we say when E is parallel to dA, we say E dot dA, they don't have to be parallel, but when they are parallel to each other, then the cosine theta becomes 1. So it's just the magnitude of E. This is the magnitude of E times the magnitude of dA. And that's kind of nice. We're just multiplying two numbers together. That's not, even I can do that. And we say, well, our flux, which equals the surface integral of E dot dA, becomes, well, if I pick my Gaussian surface right, so that E is constant. How do I do that? I make my Gaussian surface equidistant, all points on it equal distance from the charge. Remember, the electric field falls off as an inverse square relationship. If I'm the same distance away at all points on my Gaussian surface, I got the same numerical value. So, okay, because this is spherically symmetrical, because this is spherically symmetrical, I can take this Gaussian surface, I can take this E outside my integral, because it's a constant with this Gaussian surface. So I'm saying my flux is equal to E, the surface integral of dA. Oh, well, the surface integral of dA equals 4 pi r squared, hence we had it on our quiz today. And E, of course, is KEQ over r squared. We learned that last time. Shove them in. So we say the flux is equal to the surface integral of E dot dA, which equals E integral of dA, which equals KEQ over r squared. There's my E bit multiplied by my dA, my total area, my A. And that equals 4 pi KEQ. Just doing my math. The r squareds cancel. And then tradition has it that we recall from the first chapter that KE is equal to 1 over 4 pi epsilon naught. And we say, look, there's there's a 4 pi, and there's a KE, so I substitute in for that, and let's just do it. 1 over 4 pi epsilon naught Q over r squared 4 pi r squared. I just wrote that thing out again. That guy goes with that 4 pi epsilon naught. That 4 pi goes with that 4 pi. And I get Q over epsilon naught. Yes?
Are we always going to integrate over the sphere?
We integrated over the surface area of a sphere. We did that. The surface area of a sphere. All these little bits of area, when you integrate them together, give you the total surface area for the sphere. And I know the answer for that. It's 4 pi r squared.
It's always going to be a sphere.
I chose this to be a sphere. It won't always to be a sphere, but I chose this to be a sphere. So for this problem, this problem it's a sphere because I decided that. Okay, cool. So this is Gauss's law. The flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And it's really useful to know that because it's going to keep coming up and coming up. So all that work was to get that law at the end. Okay. Let's play with it a little bit. So the electric flux through a Gaussian surface surrounding a 3 Coulomb net positive charge. Well, let's have a look. I say that my flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. I'm going to write that down as many times as I can because I want to know it for the test. I want to know my flux. Oh, and I know my Q in. I got told that. So my flux is going to equal plus 3 over epsilon naught. Well, that was pretty straightforward. And the units, of course, are going to be flux. Newtons per Coulomb times meter squared. Now, I know that Q is in coulombs and epsilon naught I could look up in a book. But the fact of the matter is it's flux. And I know that flux is Newtons per Coulomb times meter squared. So that's a piece of cake. That's really nice. Let's say that I move my Gaussian surface. I want to know the electric flux through this Gaussian surface now. And I say, well, the flux is equal to the surface integral of E dotted with dA, which equals Q inside over epsilon naught. And What's the charge that's inside my Gaussian surface? 0. Now, let's just visualize that. That electric field line is going in. Is that a positive or negative flux? And that same field line is coming out. Is that a positive or negative flux? Add them together, cancel. So unless the field line starts at a charge or ends at a charge, it's going to be cancelling itself out. So this is really nice, because if the flux you get equals a positive value, you know you have positive charge inside. And if the flux is equal to a negative value, you know you have a net negative charge inside. Yeah? And if it's 0, you know there's no charge inside. So here's some examples. We have 3 different Gaussian surfaces. Gaussian surface 1 is the middle one. Gaussian surface 2 is the one at the right-hand side. Gaussian surface 3 is at the left-hand side. And we know that we have some charge inside one and some charge inside another. So we say the flux through GS1, well, it's going to be the charge inside, which is Q1 over epsilon naught. And for the through Gaussian surface 2, well, it's the combination of these two charges, so it's Q2 plus Q3 over epsilon naught. And for 3, it would be there's no charge inside. And for 4, GS4, the flux would be Q1 plus Q2 plus Q3 over epsilon naught newtons per coulomb meter squared for Gaussian surface 4. 2 coulomb positive charge sits at the center of a sphere, spherical surface of radius 6 meters. What is the electric flux through the surface? Okay, let's stop this. Let's see what people are saying. So, boom. Mainly A. So let's have a look. What would my visualization be? I draw my axes, and I have a charge here, and this is 2 positive, and then I have a sphere, and I know that that is 8 meters. And I know this obeys Gauss's law. I want to find the flux. Flux is equal to the surface integral of E dot dA, which equals Q inside over epsilon naught. And for this one, I'm not worried about the bit in the middle because I know Q inside. So flux is equal to Q inside, which is plus 2 over epsilon naught, and that's going to be newtons per coulomb meter squared. So there's my answer. So, okay, not so bad. This is a bit, it's got IJKs in it. Can you ever go at that one, please? We're back. Yep, we're back. And let's see what people put down for this. So let's stop it, and then let's do this. And mainly B, there's a little bit of scattering, but mainly B. Let's have a look where what that comes from. And what we basically say is, okay, I want to visualize. So here's my X, Y, and Z. And then I say, well, the point charge is at 2, 2, 2. So there's 2, there's 2, there's 2. So let's draw this little. So my point charge is there. And then let's change color pen so this is a bit more clear. And let's go to a black. And then for my Gaussian surface, it says the Gaussian surface 4 meters on side with the origin is 1 and the other is at 4, 4, 4. And the key question I'm trying to ask is this charge inside that Gaussian surface? And it clearly is. If you look at it from the side, that's 4 along the x, and that's 4 along the y, and that's 2 along the x and 2 along the y. If you do that on any of the surfaces, you're always going to be in the middle. So then I say, okay, well, my flux is equal to surface integral of E dot dA, big, which equals Q inside over epsilon naught. So my flux is equal to, what is my Q inside? 5 coulombs negative minus 5 over epsilon naught. And that is going to be newtons per coulomb meters squared. So, boom, 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 minus 5. B is the answer. Cool?
Why negative 5?
What's the charge?
Oh, negative, okay.
Yeah. So that's where that comes from. So we're going to take a break here. When we come back, we're going to actually use these things to find Gaussian electric fields.